Hello friends, I am Dr. Maninder Singh from Department of Computer Science, Punjabi University, Patiala. Today's lecture is on MAC protocols. In this lecture, we are going to discuss in detail about the working and protocols of medium access sublayer of OSI model. Now, let us start. The medium access sublayer is the bottom part of data link layer. The medium access sublayer is also known as MAC, that is Media Access Control sublayer. When a common medium is shared by many stations, MAC layer plays a very important role. Without this control, several stations transmitting simultaneously could produce garbled messages. The media access control mechanism standardized by IEEE are implemented in the MAC sublayer of the data link layer. It provides service to the LLC logical link control sublayer and receives service from the physical layer below it. The basic functions of MAC sublayer is the media access control, error detection and station addressing. Media access control procedures are implemented to ensure that every station gets a fair chance to transmit and collisions do not take place. There are several methods of media access control in LANs and each method is applicable to specific LAN topology. In addition to the basic access procedures, the MAC layer also handles the frame delimiting, address recognition and error checking functions. When a number of user stations share a single transmission medium, this is called a multiple access communication. The transmission medium is broadcast in nature, so all other attached stations to the medium can receive the transmission from any given station. The physical transmission medium of a LAN is shared by the stations connected on the LAN. Let us see how media is shared. The two basic approaches to medium access control are static and dynamic access control, or in other words, it is called static channel allocation and dynamic channel allocation. The dynamic access control is further categorized into random access and scheduling. The figure here shows various techniques for sharing a transmission medium. First, we will talk about static channel allocation. In LAN, number of computers are working and only one computer is allowed to broadcast on the communication channel. The first method of allocating a single communication channel among multiple contending users is by using frequency division multiplexing, that is FDM. If there are n number of users, the entire bandwidth is divided into n equal partitions and each user is allocated one partition. Since each user has been allocated a fixed frequency band, therefore, interference between them is avoided. But this scheme is applicable only when number of users are less and each has constant traffic. When number of users in the LAN is large with constantly varying traffic, then the bandwidth is divided equally into n partitions. If the number of users is less than n, then a significant portion of frequency spectrum is wasted. But if the number of users is greater than n, then some of them will not get a frequency channel due to shortage of bandwidth. In this case, channel is said to be inefficient. If all the users who want to communicate are arranged in one queue and number of users are n, then the average delay t will be n times the mean time delay. The static FDM exhibits poor performance of channel. Next method of channel allocation is dynamic channel allocation. Dynamic channel allocation method is included in all LANs and WANs. Dynamic channel allocation method is able to handle all the different types of traffic conditions. An order is built up among the stations of the LAN so that proper chance is given to each station to transmit its data frames. But for this, some requirements are to be satisfied by the LAN. First requirement is that the workstations or terminals are independent and work is generated at a constant rate. Second requirement is that a single channel is available for all communication. All stations can transmit and receive through it. Third requirement is that the workstation can begin signal transmission at any time or in a slotted time assigned to it. Fourth requirement is that if two stations are transmitting simultaneously, the signals collide with each other and resulting signal is garbled. This process is called collision. This collision can be detected by all the other stations. The collided signal may be retransmitted. The last requirement is that stations can have either carrier sensing or not. Carrier sensing is a specific electrical signal on the network. Sensing of carrier gives the status of the channel, that is busy or free. Next, we are going to discuss multiple access protocols. One feature of LAN is that its backbone is a shared channel or transmission link, which provides all users to access the transmission facilities. It may happen that two or more stations transmitting data at the same time, causing their signals to interfere and data gets garbled. So, in order to resolve these type of conflicts, a number of different medium access protocols have been developed. In order to handle the bursty nature of LAN, burstiness means the data is transmitted irregularly in bursts rather than as continuous streams. Traffic asynchronous TDM is used. The asynchronous TDM mechanism is further divided into two methods: contention method or random access method and deterministic method, or they are also called as controlled methods. Random access techniques are Aloha, carrier sense multiple access or CSMA, then CSMA with collision detection, which is also called CSMA CD, and the last one is register insertion. It is not very popular and is obsolete. Controlled access to LAN can be performed in two types: centralized or distributed. In centralized technique, master node decides which node is to access the channel at any point of time, for example polling. In distributed technique, each station is given an opportunity to transmit on the channel, for example token passing method and slotted ring method. This figure illustrates the typical multiple access communications where a number of user stations share a transmission medium. These sharing techniques are used both in wired and wireless communication networks. In wired communication, multi-drop cables are used in data networks to connect number of stations to a host computer. The host computer broadcasts information to the users on the outbound line. The stations transmit information to the host using the inbound line. This system is shown in this figure. A medium access control or MAC protocol is developed for this system. Here, the host computer issues polling messages to each station, providing it with permission to transmit on the inbound line. In radio communication, several stations share two frequency bands, one for transmitting and one for receiving. In satellite communications, each station is assigned a channel in an uplink frequency band that it uses to transmit to the satellite. The satellite sends back the signals on different frequency band called downlink frequency band. First technique is Aloha. The Aloha protocol is a contention protocol which was developed at the University of Hawaii in early 1970s and was originally developed for packet radio networks. However, it is applicable to any shared transmission medium. In a system when many users try to send messages to each other using a common broadcast channel, random access or contention techniques are used. Random access means there is no exact time for any station to transmit data. This scheme is very simple and is asynchronous. It is asynchronous because there is no proper coordination among the transmitting stations. The basic idea of Aloha system is useful to any system in which coordinated stations are competing for the use of a single shared channel. When a station sends data, another station may try to do so at the same time. the data from the two stations may collide and gets garbled. If there is a collision, then each station would simply wait for a random period of time before try again. The Aloha system is of two types: pure Aloha, which does not require global time synchronization, and slotted Aloha, which requires time synchronization. We will first discuss pure Aloha. The original Aloha protocol is called pure Aloha. In this, the whole idea is that each station can send a frame whenever it has a frame to send. As there is only one channel available to share, there is the possibility of collision between frames from different stations. The pure Aloha protocol depends upon acknowledgement from the receiver. When a user sends a frame, it expects the receiver to send an acknowledgement. If the acknowledgement does not reach the transmitter after the timeout period, the station assumes that the frame has been destroyed and resends the frame. The figure shows the frame collisions in pure Aloha. As you can see, when two frames are transmitted at the same time, there will be a collision and both will be garbled. If the first bit of a new frame overlaps with just the last bit of a frame almost finished, then both the frames will be completely destroyed and both will have to be retransmitted again after the timeout period. If all the stations try to resend their frames after the timeout, the frames will collide again. Pure Aloha dictates that when the timeout period passes, each user waits a random amount of time before resending its frame. The randomness will help to avoid more collisions. This time is called as back of time TB. The timeout period is equal to the maximum possible round trip propagation delay, which is twice the amount of the time required to send a frame between the two most widely separated stations, 2 into TP. Let all the packets have the same length and each station requires one time unit for transmission, which is TP. Consider any user to send packet A at the time T naught. If any other user B has generated a packet between time T naught and T naught plus TP, the end of a packet B will collide with the beginning of packet A. Since in pure Aloha packet, a station does not listen to the channel before transmitting, it has no way of knowing that above frame was already underway. This figure shows vulnerable periods during which packets can collide. Similarly, if another user wants to transmit between T naught plus TP and T naught plus 2 TP, that is packet C, the beginning of packet C will collide with the end of packet A. Thus, if two packets overlap by even the smallest amount of the vulnerable period, both packets will be corrupted and need to be retransmitted. Let us calculate the throughput of pure Aloha channel. The throughput S of pure Aloha is defined as an average successful traffic transmitted between the stations per unit time. The unit of time is slot time, which is the time required to transmit a frame, assuming all frames or packets are of same size. Since only one packet per slot can be transmitted, the maximum value of S is 1. When collisions happen, some of the packets are lost and part of available channel time is wasted. The resulting value of S is less than 1. To find the throughput of transmission channel, suppose the probability Pk that k packets are generated during a given slot time follows a Poisson distribution with the mean g per packet time is given by this equation. The throughput S is then just the offered load g times the probability of a transmission being successful. S is equal to g p naught, where p naught is equal to probability that a packet does not suffer a collision. The probability of no other traffic being initiated during the entire vulnerable period is thus given by P naught is equal to e raised to the power minus 2 g. Therefore, throughput S is equal to g multiplies e raised to the power minus 2 g. The maximum throughput occurs at when g is equal to 0.5. Therefore, for pure Aloha, the best channel utilization that can be achieved is around 18%. No synchronization is required for Aloha. Each station can transmit a packet whenever it has one. The disadvantage of this scheme is that it is inefficient because the maximum channel utilization is only 18% of the total available capacity. Next is slotted Aloha. In slotted Aloha, the total channel time is divided into discrete time slots and the stations can transmit only at specific instance of time. These time slots are exactly equal to the packet transmission time. All stations are then synchronized to these time slots so that whenever a station has a packet, it must synchronize exactly with the next possible time slot. The benefit of this scheme is that the wasted time due to collisions can be reduced to one packet time, or we can say that vulnerable period is reduced to half. Transmission attempts for 4 network users and random retransmission delays for colliding packets in slotted Aloha are shown in this figure. There are few assumptions in case of slotted Aloha. All the frames are of the same size. Time is divided into equal size slots. A slot equals the time to transmit one frame. Nodes start to transmit frames only at the beginning of a slot. Nodes are synchronized. If 2 or more nodes transmit in a slot, all nodes detect collision before the slot ends. Let us discuss the throughput of slotted Aloha channel. In slotted Aloha, the packets arrive in a synchronized fashion. The probability of single transmission during a slot time is P naught is equal to e raised to the power minus g. Therefore, throughput S is equal to g multiplied with e raised to power minus g. The maximum throughput occurs at g equal to 1, which is twice that of pure Aloha. This means that the best channel utilization that can be achieved is around 36.8%. Next technique is carrier sense multiple access, that is CSMA. Carrier sense multiple access is a probabilistic media access control protocol in which a station confirms the absence of other traffic before transmitting a data on a shared transmission medium. Carrier sense means that a transmitting station tries to find out whether another transmission is in progress before starting a transmission. That is, it tries to identify the presence of a carrier signal from another station before starting to transmit. If a station senses a carrier, the station waits for the transmission in progress to finish before starting its own transmission. In other words, CSMA scheme is based on the principle of sense before transmit or listen before talk. Multiple access means that more than one stations may send and receive on the shared transmission medium. The vulnerable time for CSMA is the propagation time Tp. The propagation time is the time required for a packet to propagate from one end to the other end of the medium. Now, look at this figure in which station A transmits a frame at time t1, which reaches the rightmost station D at time t1 plus Tp. This figure shows the vulnerable time for CSMA. When a station senses the medium to be idle, it transmits the packet by using one of these approaches: non-persistent CSMA, one-persistent CSMA, and p-persistent CSMA. Non-persistent CSMA is a non-aggressive transmission protocol. When the transmitting station has a data to transmit, it first senses the medium. If the medium is idle, then it transmits the data immediately, but if the medium is busy, then it waits for a random period of time during which it does not sense the transmission medium before repeating the whole process, that is sensing the transmission medium for idle or busy again. This scheme reduces the collisions and which results in higher medium throughput. Next is one persistent CSMA. One persistent CSMA is an aggressive transmission algorithm. When the transmitting station is ready to transmit data, it senses the medium for idle or busy. If the medium is idle, then it transmits the data immediately. But if the medium is busy, then the station senses the medium continuously until it becomes idle. Then it transmits the message unconditionally, that is with probability equals to 1. In case of any collision, the sender waits for a random period of time and attempts to transmit again unconditionally, that is with probability equals to 1. One persistent CSMA is used in CSMA-CD systems including Ethernet. Next is P-persistent CSMA. This is an approach between non-persistent and one persistent CSMA access schemes. When the transmitting station has a data to transmit, it then senses the transmission medium for idle or busy. If the medium is idle, then it transmits the data immediately, but if the medium is busy, then it senses the medium continuously until it becomes idle, then transmits a data frame with probability p. If the station does not transmit data frame, that is the probability of this event is 1 minus p, then it waits until the next available time slot. P-persistent CSMA is used in CSMA-CA systems including Wi-Fi and other packet radio systems. Next technique is carrier sense multiple access with collision detection, that is CSMA-CD. Carrier sense multiple access with collision detection is a media access control method used mostly in LANs which are using early Ethernet technology. It uses a carrier sensing technology in which a transmitting station detects other signals in the medium while transmitting a frame and stops transmitting that frame, transmits a jamming signal in case of collisions, and then waits for a random period of time before trying to resend the frame. CSMA-CD is a modification of pure carrier sense multiple access, that is CSMA scheme. CSMA-CD is used to improve CSMA performance by terminating transmission as soon as collision is detected. The base protocol is that a station with a message to send must monitor the channel to see if any other station is sending. If another station is sending, the second station must wait or defer until the sending station has finished, then it may send its message. If no station was sending at the time that it first listened, the station may send its message immediately. The term carrier sensing indicates this listening before transmitting behavior. If two or more stations have messages to send at the same time and they are separated by a significant distances on the bus, each may begin transmitting at roughly the same time without being aware of the other station. The signals from each station will superimpose on the channel and is garbled beyond the decoding ability of the receiving station. This is termed as collision. Let us discuss collision detection procedure in CSMA-CD. The following procedure is used to resolve a detected collision. The procedure is complete when retransmission is initiated or the retransmission is aborted due to numerous collisions. Continue transmission with a jam signal instead of frame header data or CRC until minimum packet time is reached to ensure that all receivers detect the collision. Increment retransmission counter was the maximum number of transmission attempts reached, if so, abort transmission. Calculate and wait random backoff period based on number of collisions. Re-enter main procedure at stage 1. because of quick termination of transmission time and bandwidth is saved. Therefore, CSMA-CD is more efficient than Aloha, slotted Aloha and CSMA. CSMA-CD networks work best on bus, multipoint topology with bursty asynchronous transmission. All stations are attached to one path and monitor the signal on the channel through transceiver attached to the cable. CSMA-CD has totally decentralized control and is based on contention access. CSMA-CD supports both baseband and broadband system. CSMA-CD offers 4 options in terms of bit rate, signaling method and maximum electrical cable segment length. These are 10 base 5, 10 base 2, 10 broad 36 and 1 base 5. The numeric field in the beginning indicates the bit rate in Mbps. The middle term indicates the type of signaling system, that is baseband or broadband. The numeric field in the end indicates the electrical cable segment length in multiples of 100 meters. Manchester signal code is used at the baseband level of transmission. In broadband transmission, different phase shift keying is used to convert the Manchester encoded signal into analog form. So friends, this was all about MAC sublayer and MAC protocols. Hope all the concepts are clear to you. Hope to see you in the next lecture. Till then, goodbye. Thank you.